All right, thanks, Sandeep. Yeah, so there's a poll in the Discord channel. Basically, for this session, this is kind of an impromptu session, so bear with me as I wing it. But we're going to be building a toy effect system in Scala, and there are a few options. We could do monad transformers, or free monads, or tagless final, or reader. Looks like reader is the winner, and that's my personal favorite, so I'm happy with that. So let's do it. I'm keeping an eye on Discord, so feel free to drop any questions anytime. This is very, very informal. Otherwise, I'm just going to be kind of talking through what I'm writing. Also, in the interest of time, since we only have 30 minutes, I'll do, rather than just making everybody watch me type in real time, I'll copy and paste little blocks of code and then kind of explain each one as I do. So to set this whole thing up, we want to build an effect system. And really, if we back up a little bit, we want to build a functional program that is itself a pure value. Our effect system is what will take that pure value and run it and actually make it do something. Again, in our little toy world, we have to have a toy program. And so our toy program is going to look something like this. And by the way, how is the font size?
I think you may need to zoom a little bit. Yeah, that's brilliant.
Let's see, can I move this down? Does not look like I can. Oh, there we go, perfect. Okay, cool. So here's an example of a program, an imaginary program that we want to be able to write. We can't write this today, this wouldn't compile. But basically, we want to be able to produce programs that are pure values that represent a sequence of imperative instructions, really, to take. So here's an example called en program. We don't know what the type is because this is imaginary, but we want to be able to write in this style. So here's a program that says, first I want to write, so that's probably printing to the screen, a string, so asking user for their name. Then I want to read, probably from the keyboard, a line of text, and that'll be the person's name. And then finally, I want to write hello name back to the user. So very, very simple I/O program. But we want to write this without doing any actual like printlns or system.in.read or anything like that. No side effects. We want this just to be a pure value. And then to add a little bit more to this to make it more interesting, here's the exact same thing, but in a different language. So again, we're writing, reading, and writing again, but in a different language. And then I'll add one more program here that chooses between them based on an environment variable. So the first thing that this one does, again, this wouldn't even compile, but if this could work, what this does is first read the lang environment variable. And if that starts with ES, then we'll run the ES program. Otherwise, we will run the EN program. So each of these programs would probably have the same kind of a type. It'd be a program for some kind, type program that we need to create of unit. So we're printing to the screen, reading from the keyboard, printing back to the screen, and not returning anything interesting at the end. It's just a unit. So that is the setup. That's the framing of this. That's what we want. We want to be able to write programs that look like this. And to do it, we're going to need an effect system. So in other words, we're going to need a way to interpret this code as a bunch of effects. And in this case, when I say effect, I essentially mean computational effects or side effects or I don't know, interesting things for the computer to do. And specifically in this code, there are three essentially classes of effects. We have an effect that has to do with writing information somewhere, probably to the screen. We have an effect that's about getting information from somewhere, probably the keyboard. And then one more effect that is about reading information from somewhere else, in this case, just the system environment that the program is running in. So we have three different effects. So we're going to write an effect system using free monads that give us these three distinct effects that we can then compose into any kind of program that we like, that again is itself a pure value. So I'm going to leave this here, but I'm going to comment it out because it will not work yet. And then we'll actually start to build this thing up. And I understand that the bottom of the screen might be a little bit cut off, so I'm going to just scroll a little bit. Okay, and if we can get through this thing quickly enough, we'll do two versions. We'll do a from scratch version of this, and then the same thing but using Zio, because the effect system that we're going to use, the style that we're going to use is the reader monad, which if you squint and simplify quite a lot, is what Zio is. Okay, cool. So just to start off, we'll create our definition of a reader monad. So this is a reader. It's a pretty simple class. It's got a map and a flat map, so it's monadic. And it has two type arguments and one field called run that's a function. So this says that reader for some type E and some type A abstracts over a function that takes an E and produces an A. And the common way to think of this is E is some environment, or it's something that is needed for this run function to run. And A is the type that it produces. You may often see this as thought of as dependency injection, where E is the dependency that run needs. E is the dependency that needs to be injected to actually make the thing run and produce the A. So anyway, it's no more complex than that. It's just a wrapper. It's a case class wrapper around a function of type E to A. And then we have a couple of functions so that we can combine reader with other stuff. So if we've got a reader which abstracts over a function E to A, and we want to operate directly on that A, we just use map. And this is a very standard pattern. So we've got a function that, given an A, produces a B. Map will let us turn our reader EA into our reader EB. I'll skip over how that works just in the interest of time. And then flat map is the same sort of thing. If we have a function that operates on the A that this reader would produce, and when run, it produces another reader that takes some other type of environment and produces some other type of output. Flat map lets us apply this function to this function to give us another reader. One little tricky thing here is that the environment type of this reader that comes out of the flat map is a subtype of the environment that we started with. So it sort of abstracts over the original environment type and potentially adds some more information to it. And we'll see why that's useful in a second here. So let's create some effects using this style. Our first effect will be about reading from the environment, reading environment variables. And we'll create a trait called hasEnv. And it just has a method env that gives us a map of string to string. So this is our environment. So if we have this map, we can look up any environment variable that we like. Let's see. Now let's make that into a reader with this function. So this is a function that says, if you give me the name of an environment variable, I will give you a reader, which is just an instance of this case class. So you give me a name of a environment variable that you want, I will give you a reader that given some kind of class that extends hasEnv, I will give you a string. So basically this creates a continuation that given an environment that is a subtype of hasEnv, we'll be able to look up the environment variable that we're looking for. And very simply, it just calls .env on our environment because that must be a method of the environment if it's a subtype of hasEnv, and passes name. And so the type of this thing is reader of E string, where E is a subclass of hasEnv. All right, keeping an eye on, please ask questions in the Discord as they come up, and I'll keep an eye on that and answer them as I can. Okay, let's see, we're 10 minutes in, cool, so we're doing well on time. I'm gonna repeat this pattern for read lin and write. So here, maybe I'll visually separate these, just so this is a little bit easier to follow. Okay, so here's the exact same thing, but instead of an effect that gives us a way to look up environment variables, this is an effect that gives us a way to read strings from somewhere. And we call it hasReadLin. So anything that is a hasReadLin has a method readLin that produces a string when we call it. And then similarly, we have a function here to create a reader out of it. So if you call readLin, this will return a reader that takes some environment who is a subtype of hasReadLin and produces a string when provided that environment. And the way that works is given the environment, which is an E, which is a subtype of hasReadLin, it produces a string, which is just achieved by calling readLin on that E. Cool. And then one last one of these, and that will be our write effect. So same kind of thing, except our hasWrite effect gives us a way to, given a string, write it somewhere, and then it returns nothing interesting. So otherwise, it's the same. So we call write, we give it the string that we want to write, and it returns a reader that needs an E, which is a subtype of hasWrite, and given that E, it can call write and provide the output. And so far, we haven't actually implemented the way that we're going to read from the environment or read from the keyboard or write to the screen. None of that has been defined yet. That actually is really useful for testing, because we can wait until we want to actually run our program and provide different implementations of those things. So for example, in testing, it's probably not convenient to be reading from the keyboard and writing to the screen. We want something a little bit more deterministic than that. And this pattern will give us that option. And actually, we're going to need it since we're in this scasty environment. We actually don't have a standard in to read from. So we'll have to sort of fake it. Okay, so that is really, that's almost everything we need. So our next step is to write our program. So the thing that we started with that's commented out up here, I'm going to paste that again, but with types this time. But otherwise, it will be exactly the same thing. So here's our first program. Our first program has two effects. It has writing and reading from standard in. So our reader, the type of this thing is a reader, and its environment has those two effects. So it's a reader that has an environment with hasReadLin and hasWrite, meaning to run this thing, we have to give it a way to read and a way to write. And the return type of this effect is unit, and that comes from here because we're not actually doing anything with any of the data. It's just I/O. This program, exact same thing, just different strings here. And then this program gets a little more interesting. So our environment type gets even bigger. So program is a reader, and unlike these two programs, its environment has three different sort of effects in its type. So for program to be able to run, we have to give it an environment, or an E, that is a subtype of hasenv and hasReadLin and hasReadWrite, or sorry, hasWrite. And that way, to run this thing, we'll have a way to look up environment variables, and we'll have a way to read text, and we'll have a way to write text. And I think that's about all there is to say about that. Oh yeah, so here write, readLin, and readenv, those are those functions that we wrote here. So here's readLin, that's in those four comprehensions below. Here's write, and here's readenv. Those are when you see these functions here, that's what they're referring back to. It's these ones that we wrote. So they're returning readers. And we can use this in a for comprehension because a reader has a map and a flat map. Okay, so if we try to run this, it will compile and it will run, but nothing will happen because we haven't actually defined a way to run our program. We've only defined a way to build up our program. But that's what we set out to do originally. We wanted to represent a program as a pure value. So this is a reader, which is a case class. and that's really all it is. So our program can't actually run. We have to come up with a way to run it. But if you remember, a reader does have a run field in it. So a reader is a case class, and it has one field called run. So we can call that run, and we can provide it the E that it needs, the environment that it needs. So let's do that. So we're going to take our program, and it's going to be this one. So we have 3 programs. We have N program, S program, N program. We're going to run this third one. So when we say program.run, we're just dereferencing that run function that's an E to A, where E is this type and A is unit. So to run it, it's just a function, and we have to provide it with an environment of this type. And so that's what we do here. So we're just creating an anonymous class that has that type. So this is a new hasEnv with hasReadLin with hasWrite. And to make that compile, we just have to override those 3 methods, one for each of these effect types. So to read from the environment, we just look up, we need to get a map of string to string that will represent our environment. We've already got that. It's provided by the standard library. So we'll just use sys.env for that. For readlin, we want a way to get text from the user. Normally, we would do this. This will read from standard input. That's not going to work in this Scala environment. So I'll just make it always return James. And this is an example of, we can change our implementation based on what we're trying to do. In this case, we're trying to run on Scala, but if we were running from a test, we might have a list of strings that we want standard input to look like, and we might have a data structure that we want to store into for when we write that we could then later inspect. So for writing, we can use print because this will give us standard out down here, and that should be it. So I guess if there are no questions, let's give this thing a run. And it's not interactive because I'm not typing anything at the keyboard because of this line, but here you can see the output. So it says, "What's your name?" And that happened here, and then it read from standard in, which just got this string here, and then it wrote hello name, which is right here, and we can force testing the other path. By overriding so instead of using the system environment, we can make our own. So we'll say our system environment variables are lang is something like that. Should work. And so now we see the other program being run. Cool. So that's really all there is to it. There's not too much boilerplate, which is part of the reason I like this approach. We have our reader monad, which you can find in pretty much any functional programming library, whether it's Scala Z or CATS. And then we just have to write these traits that represent our different kinds of environments that correspond to the different functional effects that we want. And then these sort of convenience functions to create instances of reader that match the right environment and do the right thing. And that's pretty much it. This is way more simplistic than Zio, but philosophically, it's the same idea. This is essentially what Zio does. Zio gives us a lot more. It gives us, completely aside from the runtime that it gives us, it's more than just a reader. Sorry, let me scroll up here. It's more than just a reader with an environment and an output. It also has a third parameter. So R, I think, is what they call the environment, and then E is like an error type, and then A would be the non-error result, which is pretty handy. So you can actually encode the potential errors that could result from your effects directly in the type of the effect itself. So we've got 9 minutes left. So I think if there are no questions, we can do a really quick version of the same thing, but using, using a little older version of Zio, because that's what I have on hand. But before we do that, are there any questions on any of this code while we've got it here? And feel free to drop those in Discord.
Yeah, Discord is
All right.
quiet.
Yeah, very quiet. Cool. Well, then I will, let's make a new one of these. So we're going to use Scala 2 with this now kind of outdated version of Zio. Extra SPT. Ah, here we go. So we'll use an older Zio 1.0. Zio's up to 2 point something. Actually, I don't know if their 2.0 is shipped yet. Might be a release candidate. Anyway, 1.0 is kind of old, but that's okay. We'll get the idea. So because we're using Zio, we don't have to define reader or any of that stuff. So we can define our has-env, which looks exactly like it did before. But to construct that, rather than creating a instance of our reader case class, we're going to create a Zio. So here's the signature that I was talking about. So Zio is like reader. It's like the single effect type in Zio. And an instance of Zio has 3 type parameters. It has the environment type that it needs to be able to run. And that's exactly like what we had. It also has the error type that it could result in. And it has the return type that it will produce if there's no error. And then this is just the incantation to construct a Zio with this shape. Okay, and then I guess I'll just sort of quickly paste these other 2 because they're not really dissimilar. So here's our readlin, very similar to before, and then here's our has-write. So this is exactly what we had before. The only difference really is the way we're constructing the Zio versus the reader from before. But our traits look the same, which is kind of nice. All right, and then that's it. So now we'll do our 3 programs that we had before. And let me get this away from the bottom of the screen a little bit. All right, so this looks pretty much exactly like it did before. The only change is instead of reader, this is a Zio.Zio, and we've added this 3rd type parameter for the error type. Otherwise, this is the exact same thing we had before. And then running it looks pretty similar. With Zio, we have these runtime environments because Zio has lots of support for fibers and async and threading and parallelism and all kinds of good stuff. So we'll get a runtime from Zio, and so we'll just get the default runtime, and then we'll say I want to run. I want to actually run and this is a function that takes a Zio and runs it. So I want to run my Zio, and provide is a method on a Zio, on an instance of Zio, that lets us inject the environment. So provide is just like our run from before. And then we have this extra layer of having the Zio runtime actually run the thing. But otherwise, it's the exact same thing. We construct a new has-env with has-readlin with has-write. And then we define our 3 ways to do those things. And so just like before, this is not going to work. And that should be all we need. So let's give that a try. Hopefully this works with the Zio library. I have not actually tried this before. Hey, it worked. What do you know? So anyway, that's a really quick overview of what Reader is all about and how Zio is a very sophisticated, well, this doesn't show the sophistication, but Zio is a very sophisticated extension of that idea. What else have we seen? We've seen that this lets us represent programs functionally because this this program is just a value. It has no actual behavior. And the behavior comes from here. I think that's about all I've got. Are there any questions?
Nothing on Discord.
Cool. Well, I think we can call it, and I'll jump over to the spatial chat in case anyone wants to talk about this. I can also point you to some other examples if you'd like to compare this to tagless final or free monads or monad transformers or anything else.
Just so you know, people, we have 3-4 minutes, so you can actually ask questions on Discord before, and someone is typing, so hopefully we'll see something come up.
Oh, you scared them away.
Oh, that was Lavanya. Okay. It's about our previous one. Actually, same friend is typing.
The question is that I said reader is my favorite and why. That's a great question. The short answer is that I'll just go through the 4. Well, actually, I'll go through 6. So monad transformers is it turns out to be extremely noisy. The code is not fun to maintain. It's just a ton of boilerplate, and the type signatures are horrible, and it's just really unpleasant to work with. Free monads is actually pretty nice, but it's a little bit inefficient because it has lots and lots of allocation and garbage collection, and there's lots of instances of case classes wrapping instances of case classes. Tagless final is a lot better than free monads, even though they're, I learned from Sergey Winitsky, who's at this conference, that they are equivalent. One is the church encoding of the other. Tagless final, so it solves a lot of those problems with the performance of allocating lots of case classes, but it relies on a hierarchy type pattern that's a little bit confusing, especially to newcomers that I've trained in the past. But its benefit, to me, one of its main benefits is it's very popular, especially in the type level ecosystem. So it's probably worth learning if you're going to use any of that stuff. But if you have the option of not doing it, then it's a level of complexity that you don't need to worry about with Reader. And so I guess that brings me to Reader. I like Reader because it's very, very simple. It's straightforward. For me, it's easy to understand. And I would not use the Reader that we wrote here in production. It's not going to be efficient, and it's probably going to blow the stack. But the pattern is very easy for me to understand, and I find it very approachable. And it happens to be the way that Zio works. And so Zio is, unlike my Reader implementation, Zio is very much production ready and has a lot of features that I like. So I think in part, my answer to why Reader is certainly I like working with Zio. But also I find the simplicity and the entry cost to be very low. The simplicity to be high, the entry cost to be low. And then 2 other patterns that I did not talk about today are M and F, and that's just because they're over my head and I can't, I don't understand them yet. So maybe next year.